So again, homework can go in the box if you have it. This box is over here, but if you're here, don't worry, you can hand it after class. It'll count for at the beginning of class. All right, so I said the homework's due today, so hopefully everyone's that's turning in are going to use some late days and almost ready, because you don't want to use too much of those in the first homework, I promise. But went okay, sort of seemed all right. Okay, you know, we try to sort of adjust as time goes by if necessary to fit the level of the course. So, you know, this is a small course. If it was just way too hard and you think that there were issues, let me know, because we're trying to make it so that everyone can do these things. But I think, I mean, there actually weren't that many people office hours, so that's either a good sign or a bad sign. I'm not quite sure which one, but hopefully a good sign that everyone just understands it and can just work along. But you can still, the solutions won't be out until, normally I do it, actually no, I won't do it until a week from now, because I want people to have a chance to hand in to use the late days up before the solutions are posted. And once the solutions are up, then obviously you can't turn it in after that. So I will turn out the solutions next Tuesday. Oh, remember, we're not having class next Wednesday. So maybe also, or next Thursday. So let me just write that over here. It's not on the video, but so no class Thursday.
Like
this, yeah, 2 days from now, no class. I'm giving a presentation in San Diego. So no class this Tuesday. And because of that, I'll actually both release the solutions and the next homework next Tuesday. There were a couple things that are going to be covered in the next homework that I didn't want to put up until we had covered that. So we're not going to release it until next Tuesday. We probably actually won't get to quite all of it, but it'll be then probably the next Thursday that we'll get to all the material. And I want to get the homework out there so we have definitely plenty of slack time, but I don't want to push it too far. So what we're going to have to talk about today, though I'll actually answer one question that came up before class too. Today we're going to finish up our unit on machine learning, really, and we're going to start our power systems unit. So I'm going to finish up. We have like 5 slides left talking about evaluating ML algorithms. Then I'll talk about this paper I had mentioned the time before, which is on applying, this paper I wrote about 2 years ago now, on applying machine learning algorithms to predict individual house energy consumption. And again, I'm sort of putting this paper not because I think it's the best example of a paper or anything like that, but it is an example of a paper where fairly simple machine learning techniques come up with some pretty interesting results from an energy standpoint, from an applied standpoint. So if you want to do things like this for your class project, I can point you in the direction of some data sets. That also I will address more on Tuesday in terms of the proposal and everything like that. The proposal for itself is quite short, but we want to get that at least rolling. So start thinking about that a little bit more. Though we can talk more about that on Tuesday. And then, as I said, the final thing we'll do is we'll start our unit on electric power systems, which is going to be the second of the 3 main topics in this course. So before I jump right in, a question came up about, so as many of you probably saw, sometimes, even for data that isn't that big, the solvers you guys were using, which was YALMIP, and I guess you also, well, sorry, YALMIP is the sort of the general framework that library we're using to solve these problems, and then the solver that you use was called Sedumi. If you used it correctly with the tag, apparently it no longer does by default anymore. So one thing you may have noticed there is, first of all, that the MATLAB solver is much slower. So you almost have to use Sedumi, or it would just take forever on some of the longer problems. But on some of but even Sedumi itself takes some time, right? And basically, you'd see it sort of start to churn out, and it would kind of print a line and then wait several seconds and print another line, et cetera. And the question was, first of all, are there faster solvers than YALMIP? And secondly, than Sedumi? And secondly, what is YALMIP doing versus Sedumi? What are these different things doing? Because it takes a lot of time even to get to the point where it starts printing out anything if you use Sedumi. So first of all, yes, there are faster solvers than Sedumi. Sedumi is very nice because it's very general purpose. It can solve almost any problem, and it's also free. So those are 2 sort of very nice things about it. There is a very large range of commercial software that does also solve optimization problems, though. A lot of it is free for academic use, but you have to jump through some hoops to actually get the software as an academic. So a very common library for, this is only for linear and quadratic programming, can YAML use it. But if you have linear or quadratic programs and your problem can be reduced to a linear or quadratic program, this library called Cplex is kind of an industry standard. It's very expensive if you don't have an academic license, so it's not great to get dependent on it, because if you go out into industry then you want to use it and all of a sudden you find you can't. But it's very fast, and for sort of tests, if you do want to go out and try to install it, I use it for most of my linear quadratic programming when I want to do something on the relatively quick side. So it's definitely nice. The other question, though, was what was YALMIP doing versus Sadoomi? Because you would type something like this, right? You type solve SDP with your arguments here, and then it would just kind of wait for a while, right? And if you had like a CPU monitor, you'd see that it was doing stuff. So the CPU is being used up, but it would just kind of wait for a while. Then after about, on the last one, it would take like a minute or two before it would do anything. And then after 2 minutes, it would, type out Sadoomi. And then you'd have all these lines come out with like, iteration 1, blah, blah, and you have some error, -2, 2, some error. And these would sort of take their own time to solve. So what's happening here is that the time before Sadoomi starts outputting stuff, that is the YALMIP library converting your problem to one in standard form. So solvers, things like Sadoomi, they only solve problems in this standard form I was talking about, right? They're solved things like this, like min of C transpose Z subject to AZ equals, or AZ is less than or equal to B. It's slightly more general than that. They can also have equality constraints and things like this. But virtually all solvers require a standard form like this to the problem. And if you remember, we have to jump through a lot of hoops to get a problem like the absolute loss minimization into standard form. And you do the same thing for the epsilon loss or the deadband loss on the homework. So that is what this step here is doing. This time between here and here is taking your text problem where you write minimize this function, or you write sort of the objective here, and converting to standard form. And it does that by a set of sort of sequential rules, which are oftentimes not the most optimal way of doing it. You can actually do it a little bit better yourself. Certainly not as fast as doing it yourself, because you can do it very quickly if you sort of write that code yourself. But what this part here is doing is this is converting your text problem here to standard form. Once it starts actually solving things, that's then the actual sort of math crunching. It's kind of like Newton's method. It's not quite, but it's actually pretty close to Newton's method to actually solve this problem. It's actually very similar to Newton's method with when you just penalize some of these inequalities here instead of treating them as absolute constraints. You treat them kind of as soft constraints, and you use Newton's method on this problem. That's actually very similar, close to what it's actually doing. So that's the basic idea of what's happening here. It's first converting to standard form and then using Newton's method or something very similar to solve this problem here. So that sort of hopefully clarifies some of that, and also maybe why certain parts would take a long time. The reason why this would take a long time here is you just have a lot of data, and it sort of doesn't have the most efficient rules for converting these things. It does pretty well. It's sort of amazing how well it works considering how general purpose it has to be. But it takes some time to go to standard form, and then it takes some time to solve it once you're in standard form. So that's what was going on in that time. And that's why if you didn't use Sadoomi, first of all, the MATLAB solver won't ever print anything when it starts, so you don't know when it started. And then it takes a lot longer, so you just sort of type it in and you wait for 20 minutes and nothing happens. So sorry about that if that did happen. I think it used to use Sadoomi by default, but this has since changed. And now it's more intelligent and uses a slower, unfortunately, solver. They're not always slower, but they are slower for the problems that we're using here. OK, were there any other questions about this? OK, cool. All right, so let's then finish up our unit on evaluating machine learning algorithms. So remember, at the end of class last time, I was talking about two things we will want to do for a machine when we run a machine learning algorithm. First, we're going to want to find some notion of how the error, the residuals themselves, not the losses, but the residuals are distributed. And that was this thing here where you can say compute the variance or just plot the histogram, right? Because the histogram itself, this visually tells you a lot about what these errors look like. Are they uniform here with a couple spikes out there. No, you sort of hope this looks something like a Gaussian or something like that, but it doesn't always. But you can also make things like estimate the variance of the distribution, which would maybe give you some notion of about how widely distributed these errors are and things like that. These residuals, I guess I should say. But the second question is, if I have an actual loss function, and I want to report my loss on the test set, for example, right? Because this is an evaluation of how well the algorithm's doing. How do I actually go about reporting that? And I'm showing here now the plot of the loss itself. So this is a histogram. In this case, it's actually just kind of the former one where it's all on the positive side, because I'm just taking the absolute loss here. But really, this could be any loss function. And this histogram here has values greater than 0, right? Because losses themselves are always greater than 0. They can never be less than that. So unlike the past one, this one has all its data on the positive side. So now we're plotting the actual losses themselves as a histogram. Okay? And now, when you do something like evaluate the test error, you take the mean of these losses, right? So that is the mean of this distribution here. So it may be somewhere here. But it's important to realize what you're doing is you're sort of looking at all these actual losses and doing something with that set of losses. And so a question we could ask ourselves now is, how confident are we in these losses? Or in this average loss that we predict, right? So we say, OK, we have an average error of 0.2. Well, how certain are you that that's actually reflects some underlying reality? So I'm going to show you one way of reporting it. And this is actually not entirely the correct way. I'll mention that what is a more correct way. But I think, honestly, if everyone did this, we'd be a lot better off in machine learning, say, than we are right now. So even sort of simple tests here that are a little bit incorrect, but that are close enough for enough data, et cetera, can really be very helpful here. So what we're going to use is something called the central limit theorem. Actually, who here has heard of the central limit theorem before? OK, pretty much most people at least. The idea here, and this is a really powerful tool in statistics, is that if you take any collection of random variables, they can be distributed however you want to be. That's not quite true. But for the purposes of our discussion, they can be distributed however you want. Take any collection of random variables. And now look at the mean of these random variables. The mean itself, so if you think of the mean itself as a new random variable, so basically you take all your z's. Here z's are some samples from some distribution. They're independent and identically distributed. That's the one condition. They can't be off from different distributions. They have to be from the same one. But they're independent, identically distributed. And they are from any distribution with the mean being mu and the variance being sigma squared. This does not have to be Gaussian. I mean, this, if you look at the distribution here, this is not a Gaussian distribution, right? This is just some distribution that's, doesn't ever go below 0, has all these issues. Still, if you look at the mean of these things, so you take the sum of all the z terms and divide by the number of them, that mean itself will tend toward a normal distribution. Everyone knows what a normal distribution is here, right? So you at least have seen that. OK. So this is sort of an amazing property. You wouldn't necessarily expect this to happen, right? Because it doesn't matter how they're distributed. It's just that when you sum enough up and divide by the total, somehow that becomes normally distributed. We won't prove that, but it's a pretty basic fact. And so what we also know is that for a normal distribution, remember the probability density of normal distribution looks something like this. So I'll just draw like a standard normal here. This is 0. For a normal distribution, about 95% of the probability mass lies within 2 standard deviations. So this is 2, and I'll even write the correct. It's more like 1.96 standard deviations. Where this is the standard deviation. It's the square root of the variance. 95% of the probability mass lies within this gray portion here. So what this means is that we now have a quantity, namely our average of these random variables, which in our case will be the average of the losses. This quantity is normally distributed, tends towards a normal distribution, and we can estimate its mean and its variance. And that lets us say that with a certain confidence, again, being a little bit abstract here, or not abstract, maybe vague here, because I don't want to. Confidence intervals are often thought of in the wrong way, and I don't want to sort of make them out to be like things like probabilities or anything like that, because they're not probabilities. But what we're going to say, actually, maybe I'll just show the next slide. So what we're going to do is we're going to take all our errors, and we're going to estimate two things. We're going to estimate the mean and the variance of our errors. So what we're doing is we're going to this histogram here, not the one before, but this histogram, and computing the mean and the variance of this guy. Okay? Then, and those are those first two things. The form estimate of the mean, I'm going to call that mu hat. That's going to be 1 over, it's going to be the average of those losses. And then we're going to form an estimate of the variance, which is just the loss minus the mean squared, the average of those terms. And now this is the important part. We're going to say that with 95% confidence, the true mean, the actual mean, that does not mean the error will lie with, like for any given new example, the error will lie within that range. What it means is the mean of these errors, we say with 95% confidence that that mean lies within this interval. It's 1.96, so that's almost 2 standard deviations, where this is our estimate of the standard deviation, divided by the number of examples, the square root of the number of examples. And it's important where this term comes from. So remember, the law we had before was that the mean of this thing goes to a normal distribution with mean mu and variance equal to the variance of the actual random variables divided by the number of samples. Okay? So that means that this quantity, 1 over m prime, sum from I equals 1 to m, of the loss between our prediction on the test set and the actual thing on the test set. This whole quantity here goes to a normal distribution with mean mu and variance sigma squared over m prime. Okay? So if we want now to look at the standard deviation of this thing, the standard deviation of this thing would be just sigma over the square root of m prime. That would be the standard deviation of this quantity here, where this quantity is now approximately normal. So what we do is we just form estimates of these two things. That's just the sample mean, the sample covariance. We will divide by m square root of m prime to get an estimate of the variance of this mean. And then we say with 95% confidence that the true mean, this might not be the true mean, because as we get more data, there's some finite amount of data effects here going on. But as we get more and more data, this will approach closer and closer to the true mean of whatever this quantity really should be. And we can judge how close that is by exactly this amount here. Does that make sense to everyone? Because it's a little bit, there's sort of two things that's important to see the difference here. There's the standard deviation of the losses themselves, right? There would be the standard deviation that you compute from this thing itself. Right? That's one term. And the other term, the one that we care about, though, is the standard deviation of the mean. That is the standard deviation of the new variable that's the average of all these things. And so what we're saying when we say something like this is we're saying, I don't know anything necessarily about my distribution of actual losses. This is not saying anything about the distribution of losses themselves. What this is saying is, if I take all my losses and compute the mean, say I were to do that with 100 different test sets, or ideally a test set of infinite size, the mean you would get for that test set of infinite size with 95% confidence lies within this range here. So that's what the 95% confidence interval is saying in this case. Now, before I go too much further, I should say this is actually not quite correct, this procedure. There are a few things we did wrong. Technically, we should actually be using a different estimate for the variance. Because both the mean and variance are unknown, you should actually be dividing by 1 over m prime minus 1 there. This is something you may have seen in stats courses. If you've sort of seen the formula for doing this before, you've probably seen it with m minus 1. And we should actually also be using what's called a student t-distribution rather than a Gaussian distribution. When you don't know the variance, actually they don't quite approach a Gaussian, they approach a student t-distribution with some number of degrees of freedom. For large enough m prime though, these things are really, really close. And so for all practical purposes, we'll just say, we'll use a simpler one here. When m gets to at least 30 or 50 or so, they're pretty close, these two estimates. But this will actually be a little bit more, you'll be a little bit overconfident. So your confidence interval will be a little bit narrower than it should be when you use this procedure here. But just know that. And so in fact, there's actually much better ways in general of doing these kind of things, having significance of results like this. But this is a pretty good first approximation. And you would not, you won't be looked at funny if you use this result to report your errors in the paper, say. This is fine. Certainly, it's actually much more correct than what a lot of people do. What a lot of people do is just compute the standard deviation of this thing and show that as an error bar. So like, they'll show something like, they'll show the mean of this, so they'll say this plus or minus just this guy, plus or minus sigma hat, mu hat plus minus sigma hat squared, maybe 1.95, 1.96 sigma hat squared, and not divide by m. And this is not really an important quantity here. This is essentially showing the standard deviation of those errors. What this might be showing is, how likely are the errors, the losses themselves, to lie within a certain range if those losses were themselves Gaussian, but they're not going to be Gaussian. So this is not really that meaningful a quantity here. What you really want is this one, because this is the one that's Gaussian, and you're showing standard deviations of the mean itself. So follow this little rule here, at least be a lot better than what a lot of people do. OK. So the last thing I'll say is that when you report errors, it's also really important to report them relative to some meaningful baseline. And this is also where confidence intervals help you a lot, because this tells you, do I really think I'm better than this other, a simpler model, say. So a really simple thing to do, for example, which you should always compare to, is I have my set of features, phi, and I make my output prediction as, I should write this as my prediction on this equals phi xi transpose theta, where I've learned theta from whatever machine learning algorithm I have. I've constructed careful features here. Everything looks good. But here's a simpler set of features, namely phi of xi equals 1 for everything. So just one feature that's equal to 1 for everything. This is sort of a 0-degree polynomial you can think of it as, but really it's just a constant term. So what this is doing, actually, does anyone know if these are your features? So that means if phi, actually I forget this is the homework or not. This might be on the homework now that I think about it. No, I don't think it is. So if phi is a vector of all ones here, oops, I don't know why I put 0 there. If these are all ones, does anyone have a guess what the least squares solution would be? So it's going to say that theta star still equals this, phi transpose phi inverse phi transpose y. Does anyone know what that is? Yeah. It's just, this is 1. So this, I'll just replace them with 1s. So 1 transpose 1. That's just going to be equal to m, the number of examples you have. So this is going to be equal, and then 1 transpose this. This one here is going to be the sum of all the examples. This guy here is going to be equal to m always, because there are m entries in that vector. So this is going to be equal to 1 over m, the inverse of that thing, sum from I equals 1 to m of yi. So theta is just your average of your y values. So your prediction here is going to be 1 times the average. This is going to be, you predict on everything just the average value. Okay, so this is an obvious baseline, right? Don't learn anything, just predict the average you've seen so far. You should always compare to this, though, because if you don't compare to this, you know, if I say I get 0.1 error, 0.1 root mean squared error, well, is that good? Well, if predicting the average gets you, 0.11, it's probably not that impressive if you got 0.1 with your fancy machine learning algorithm, right? And in fact, what you really should do is always show the error you get for this predictor with confidence intervals, and then the errors you get for other predictors with confidence intervals. And it's only, you only can say to some extent that you're certain that this is a better predictor, or you at least are confident this is a better predictor, if the error bar, if the estimate, the error in one case lies outside the confidence interval of the other one. So I'm showing that here, actually. What I'm showing here is the error in predicting, this is back to our example of predicting the peak demand from temperature. So if that's your prediction task, and you use a 0-degree polynomial, so in other words, you just predict the mean of all the demands you've seen so far, your error is 0.24 plus or minus 0.0039. That would be essentially, do I have that plot here? Yeah, that would be this plot here where you just take the average here, you draw a straight line through. Okay, that gives some error. It's not 0, it's not good, but it's not infinite error either. If you use a degree 1 polynomial, that's a straight line, you get less than that. But it's still not that much better, actually. In fact, it's not significantly better than just getting using a constant term. And that makes sense, right? I mean, when we drew a straight line through that, it actually looked very much like a straight line, like a flat line, because the thing went up in both directions, and so the straight line we drew through it was not that much better than the flat line. If we now go to a degree 2 polynomial, though, all of a sudden we'd get a big drop. And here, those confidence bars, basically the one for degree 1 is outside the range of this one here, 0.15 plus or minus 0.0013. So we can say now that we are confident, or there's statistical significance to show that using a polynomial of degree 2 to fit this data is better than a degree 1 polynomial, or degree 0. We get another gain when we go from 2 to 3. So now when we have a degree 3 polynomial, we are in fact fitting it a little bit better. And if you remember, that was kind of like, that looked kind of like one of the best ones, right? Sort of in our plot there. And it turns out that after that, you actually don't get significance after that, because after that, the error bars, the improvement you get in error, if you get any, in fact here you don't. But even if you get some, it's not outside the range of what's significant there. And just as a general statement, we say it's statistically significant. And this is a completely kind of made-up term, right? 195% confidence intervals. Well, we feel good about saying 95% confident, I guess. People use other amounts. There really are much better tests you can do than this. But this is sort of stuck for whatever reason. But basically, if you have some estimate here, you can draw a 95% confidence interval. If you have another point that's here, and this is a 95% confidence interval, you would say that this one is significantly better than that one, because the mean here lies outside the range of 95% confidence interval, even though the confidence intervals themselves overlap a little bit. Whereas this here, well, you would not say is statistically significant in this case, if that's the mean, that's the confidence interval. So what's important is that the mean of one estimate lies outside the 95% confidence interval of the other one, as far as we're concerned here. Now, just to drill this in again, this is not by any means a sophisticated way of determining what statistical significance exists in your predictors. And actually, let me give a quick example of that. So suppose that you had two different algorithms. So algorithm 1, actually, how should I do this? Maybe I'll write like algorithm 1 will be the stars here, and algorithm 2 will be the circles. And this is the example number. So I mean, does that just mean we have m examples in our test set? This goes from 1 to m. And what if you had something like this, where they each have errors, but in every case, the circle is below the dot, even though as a whole, if you look at all the data and compute just a confidence interval based on all the data for both these two things, you would find in some cases that they aren't separate. But this one's always better than the other one. So in some sense you sort of say, well, it still should be better. So there are much more powerful, the point of this is that there are much more powerful tests you can do. A very common one in this case would be something called pairwise testing. So what you do is you actually run a significance test on the difference between these two things and see if that's significant, rather than running them individually to get an estimate of the error for each one and doing that. You can look at their differences and then compute sort of, is that difference statistically significant, being above 0 or not? And if it is, then yes, they're separate, even if their confidence interval, 95% confidence intervals, as we described them here, do overlap. So there are other ways of doing this, but this, for our purposes, is actually a pretty good way of doing it, of starting at least. OK, so with that out of the way, that actually concludes basically our machine learning unit. And all I have left is a little presentation from a conference a few years back on this energy view paper. So let me switch over to that. Before I do, though, are there any questions? All right, let's see. I haven't used PowerPoint in a while, but it looks like it actually works. This is my old format for slides. All right, so I'm going to go through this quickly because I don't think the sort of, not every element here is super important. But I just want to highlight kind of the main elements from this talk I gave about, as I said, about 2 years ago now. This was a paper at AAAI, which is a artificial intelligence conference. But that conference also has a big track on sustainability and sustainability applications. This was actually in that track of the conference. What it's about doing is it's about predicting the energy consumption for a single building. So what we got for this project was it's joint work with Joe Ferrara at the Department of Urban Planning. This is when we were both at MIT. What this paper is about is trying to assess for a home how much that home is likely going to consume, and then how does the actual consumption compare to that. Okay, so the reason for this, I think, and I'll just give my little spiel here on why this is an important thing, is that suppose you're a community organizer that wants to do things like insulate houses and stuff like that, right? So you want to spray insulation in houses. The problem is, in a lot of cases, you would have no idea where to really start, right? Because presumably you want to target the houses that are worst insulated, right? But how do you know where that is? All you see is it's a big map of everything. You don't really know which places you should target to go after the most important houses in some respect. Or similarly, what if you're a homeowner and you want to be efficient, so you're going to replace all your, you have a bright idea to replace all your bulbs with CFLs. But it's still difficult to know how this will actually have an effect on your energy bill, right? Because are you already using less electricity than anyone else? Are you, how much is it really going to improve you to add these bulbs in? How do you compare with other people that are using, in similar homes? You don't really know. And the challenge in both these cases is that it's very difficult to put energy consumption into its proper context, right? Oftentimes we get our energy bill and we have no idea what that actually means relative to other people. There are actually companies that do this. I should actually, do I mention that on the thing? No, I don't think I mentioned that. There are companies that do this that will like put you how you compare to your neighbors. And that's actually what we want to do almost exactly, but we want to do it kind of in a more open, scientific, transparent way. So as I said, the difficulty here is it's proper to put it, it's very hard to put your consumption into the proper context, to understand how much energy you're consuming. Is that good or bad? I guess is the base question, right? You get your energy bill. Are you doing well or are you doing poorly? And so what we want to do is we want to use linear regression or nonlinear regression to take a bunch of features that describe your house. And those are things that are available from public data sets, things like tax assessor records, things like occupancy records for your house, that have things like the living area, the value of the house, if it's residential, commercial, stuff like that. And we want to predict how much energy we expect you to consume from that. So this is exactly like the plot we showed before, except instead of high temperature being the input and peak demand being the output, now features of the house are the input, and the output is going to be how much energy you consume, say, per month. But what's also very important here is that rather than just giving a point prediction, we do want to focus on getting some sort of distribution over how much you might consume, right? So we didn't really talk too much about probabilistic distributions in this class. We largely avoided that despite doing machine learning. But we sort of saw, right, that there's going to be some range in what you might, where you might expect your errors to lie. That's kind of the distribution of your y hats minus y's, basically, right? That's this distribution, y hat I minus yi. And so you want to know what that distribution is to a certain extent, because you want to be able to characterize people to say if you consume, say, 845 kilowatt hours in the month, you're doing badly, or if you consume this, you're doing well. Because you want to be able to tell people where they lie in regards to their expectation. And this hopefully will quantify something about, are you doing good or bad? Because if all your property records and the size of your house say that you should be using 500 kilowatt hours a month, and you actually use 800, you probably should be told that, so you can think about what you can cut down. The next step would be actually telling people what to do to cut down, but we don't go that far here. We just tell them where they lie in the spectrum. Now, as I say, there's a lot of work in similar areas. A lot of work on predicting stuff about buildings. Typically use a little bit more high-frequency data. For this, we're going to use just monthly billing data rather than kind of the stuff we did with like the plugs or anything like that, where we actually use very high-frequency measurements of power. Here, we're just going to use monthly data. And I should mention that there are several companies that do this kind of stuff. So things like O-Power, Efficiency 2.0, you might have heard, O-Power is kind of a very big one. You may have heard of them. Efficiency 2.0 is another one. I think they actually just got a little while, maybe a year ago now, like that got bought up by a different company. But anyway, a lot of companies are doing this. But as I say, they're typically done in a pretty non-transparent way, where you get a bill at the end of the month and it just says you're doing worse than your neighbors, you're doing better than your neighbors. And we wanted to run this in a more scientific standpoint to get a better idea of what this data actually looked like and how to do these comparisons. So the data set we used, which is actually, in some sense, frankly, the hardest part of this. So the hardest part of any machine learning project, frankly, is the dirty secret is the hardest part is getting the data. And not only getting the data, but getting the data in the proper form. That was actually part of the homework, was doing a little bit of that. But it even goes way beyond that, because you have to scrape the data from the web rather than get it in a CSV file to begin with at all. So what we're using here is we use the data we got, which is, and this is actually really hard to get because utilities typically won't give this away. We had access to it because there had been a partnership with the utility, the one in Cambridge, Massachusetts. And what we had was we had electric bills per month, also along with addresses. So we actually knew the exact home we're talking about and their electrical bill. For every single home in Cambridge, there are about 6,500 buildings in Cambridge, every building, so it's commercial buildings too, but every single building in Cambridge. And we also have, from the public record, we have tax assessor records and property assessments from Cambridge. So these are all freely available. You can go online and get a big database of tax records for Cambridge. You actually have to scrape that off the web. It's a pain to get, but you can go get it. And it has things such as living area, building value, residential, commercial, and many others. We have about 35 features total for describing each house. And so I'll give you the results in a second. You know, what happens when we run linear regression on this. But before doing that, and this is actually a really useful thing to do in general when you're approaching machine learning problems, is before you just run an algorithm, try to get some sense of what the data looks like. Okay, so do things like plot it. I mean, in our case, it was pretty easy to plot it because, you know, I kept showing pictures, right, because we had one input feature and one output feature. That's pretty easy to plot. But even if you have a lot of of inputs and, you know, maybe one output, I guess we're talking mainly about one output here. So you have lots of input features, though. Do things like, you know, plot the inputs with respect to the outputs, each one, and see if you can notice any pattern there, because that will tell you a lot about the data itself and kind of what this might actually look like. So here is sort of one of the first plots you can do. And so here what we're plotting is we're plotting the energy consumption of the house and building living area in square feet. Okay? And as you expect, you know, a bigger building will consume more energy. But what's actually really interesting here is that these are both log scales. So the x-axis and the y-axis are both logarithmic. It turns out, if you were just plot, and actually maybe I'll show this next one first. Maybe I'll just show this. So this is actually a better plot. This is a histogram of, ignoring the input actually entirely, just what is the total power consumption for all these different homes. And it looks, you know, it looks nice. It looks like a good, nice distribution. This is sort of, it looks Gaussian. This is kind of what we like. But again, the key thing I've done here is I've scaled this logarithmically. So it turns out if you just were to take a histogram plot of the actual energy these different homes consume, it would look like a big spike at 0 and then a couple dots elsewhere. The amount of energy we'll consume just widely varies, more than you'd ever imagine it to be. And it kind of makes sense, right? Because we're talking about, you know, buildings being some commercial buildings, some you know, homes that are 1,000 square feet, some that are 50,000 square feet. But you actually see this kind of pattern almost everywhere. So even if you say, look at this plot. So now let's look at buildings that are 2,000 square feet. It's not uncommon to have one building use 10 times more than another one, both of which are 2,000 square feet. So there's a huge variance here in this data. And what you sort of see when you look at this data, and this is kind of the point of playing with this data, is that the amount of energy houses consume varies much more than I would ever expect, at least. You know, I thought it would look maybe Gaussian on just as a normal plot, but it turns out actually there's all these sort of logarithmic or exponential effects here, where, you know, it's not that people use 10% more, it's that they use twice as more or 10 times as more as someone else. So that's really interesting, and you get that from looking at the data itself. And I'm just drawing a line here of what, you know, say 10 100-watt light bulbs would cost you. So now what we're going to do is we're actually going to use exactly what we did in class. We're going to use linear regression with features. So with these features being just the inputs. We're actually not going to use nonlinear features here. We're just going to use the inputs themselves as a feature. So linear regression. But we're going to have the output be the actual log of the energy rather than the energy itself. This is actually very important to getting these good distributions, right? Because the distribution you see looks nothing like any sort of normal Gaussian error term if you don't take the log here. So you need to take the log in order to get a good scaling of your actual output variable. But what we do then is we fit both a kernel regression model and a linear regression model to predict the log of the energy people consume. And we also use what are called non-Gaussian, and there's some error. So the idea is that the energy is equal to this prediction plus some error term. This actually corresponds exactly to just the loss function. It's sort of how you measure how far away your prediction is from the true value. And the other key thing that we had here was to use non-Gaussian likelihoods. What that corresponds in our case is just exactly using non-L2 loss, using things like absolute loss or The student's t-distribution would actually give you a different loss entirely. But basically, this is just a probabilistic interpretation of what we do when we use different loss functions. So don't, all we're really doing here is using different losses to optimize this thing. So as I say, the idea is really simple. And sometimes I'm showing this because it is such a simple paper. We just took this data. Frankly, most of the effort was collecting the data in the first place and collating all and matching house records with the things we had in our, the address we had in our energy database, because these are, of course, completely different conventions for addresses and things like that. So we have to match them together, and then compute features for the houses, and then do something very simple, like apply linear regression to predict the log of the energy consumption, where, the two big insights were use the log, don't use the raw value. We got that from looking at the data. And the other one was use non-Gaussian, use non-L2 loss functions, essentially. So here are some of the results. I'm describing this in terms of the log likelihood of the data, which is a little bit, it's sort of the probabilistic analog of what the different losses give you. If you treat these models as actually probability distributions rather than just things that make point predictions, you can come up with the probability of observing the data that you actually saw. And in our case, essentially, I'm just lower is better here. So don't worry about the actual values here, but just low. Wait, no, higher is better. Less negative is better. So basically, what I'm showing here, and don't worry about the specifics, is that as you add more terms, so if you this is essentially just predicting the mean, so you have some log likelihood there. If you use linear regression, you do better. If you use linear regression with a different loss function, you do better. If you use Gaussian process regression, which is just kernel linear regression, you do a little bit better. And then if you work to not take the log at all, you actually do really, really badly. So what ends up winning in the end essentially is kernel regression. This GP here stands for Gaussian process, which is just the same thing as kernel linear regression. Sorry, kernelized nonlinear regression. And this is the best loss of all of them. Just to show it too, if you don't take the log, we do really, really badly. So taking the log is really important here. I'm not showing it here, but so I'm breaking my own rule about the reporting error bars here, because what we did here is pairwise testing as opposed to error bars, opposed to just confidence intervals, and these differences are all statistically significant within the 95% range. So I guess the one way of describing all this is that if you use these publicly available features, you can explain about 75% of the variance in people's energy consumption. So you can't explain it all, because there are just things like personal preference, right? It's just our natural. I mean, if I use a lot of energy, I'm just going to. You can't explain that from my house's features. But you can explain a surprisingly large amount of the variance in home consumption based upon this publicly available data. And the last thing is an interesting question, I think, which is what features were actually most important? Yeah, there's a question there?
So, yeah, sorry, on the previous slide, how much better, so for GP regression, how much better did just using Gaussian likelihood versus
it did worse than this one, but better than that one.
Okay.
So it's actually really important to use this likelihood.
It actually matters.
Yeah, it definitely matters. Okay, so the last thing I want to say is one more thing you can do when evaluating these methods is to see which features matter, right? Because we have these 35 features. The question is sort of which ones are we actually using in our model? And there are a lot of ways of doing this. You can look at the weights for the different features, this kind of stuff, but we're not going to do it that way. What we're going to do instead is actually add features one at a time based upon which decreases the test error the most. There's a method called feature selection, and it's called greedy forward feature selection. And it's really simple. It's not optimal by any means. It's not going to give you the best set of features, but it's a reasonable proxy for looking at what matters the most. So actually, do I say it already? So maybe I'll just have people guess. The features we had, I'll give a few. So we have things like square footage, commercial versus residential, value of the home, and number of occupants. And does anyone guess which of these would be most correlated or the best predictor of how much energy a home would use? There's no wrong answer here. You can just yell out what you think. Okay, yeah. Seems reasonable, right? So I would have guessed too. It turns out that actually the most indicative predictor was the value of the house. Of course, that's correlated with the square footage, but you are better if you only could use one thing. You're better off using house value than you are using square footage. People who have more valuable homes tend to use more energy. So and it's the bad way too. More valuable property tends to use more energy, which kind of makes sense. It's sort of depressing because you'd think that, you know, if you have a more expensive home with the same square footage, maybe it would actually use less energy if it's more expensive. It could be more efficient or whatever. But you also probably have more gadgets and stuff if you are richer, right? So it turns out that at least in this data set, you are better off just using the building value if you want to use one thing to predict the energy. After that, the number of electric meters, which is actually the number of occupants, so, well, not quite, but like for houses that have multiple units, so for apartment homes, you actually will want to know how many different electric meters are there. That makes a lot of sense because everyone's going to have their own refrigerator, for example. Property class, is it residential or commercial? That's the next one. And then finally, after that's living area. Now, individually, they're all actually fairly correlated with the output. So this shows just, you know, how correlated each one is individually. But it turns out that it doesn't, you know, you're better off looking at, if you already look at value, electric meters, and property class, you don't get that much benefit by looking at, say, the living area. It doesn't help you that much. So this is kind of interesting. And then actually one thing we built from all this was a tool where you could look at all these homes that we had. And this is actually a mock-up because I don't want to show the true thing because there's some privacy issues. So we have the actual tool for the real things, but this is just sort of coding them fake colors for now. Where we look at all the homes in Cambridge, and you could click on any one, see what it actually used, and then also see where that home's consumption compares to its mean. So, you know, given all the features, you expect some distribution over the consumption in this house. Where does this house lie in relation to that? This may or may not be still available, actually. I don't know if it is. Basically, we developed a tool where you could go and plug in your own bill for the month, and it would tell you, you know, how well you're doing, how good or how bad you're doing. So that's really it. You know, some last points. There still is a huge variance in the amount of energy homes consume. Even accounting for all these things, it's not uncommon for one home to use 10 times more than another. So we're not talking about, you know, 20% more, 20% less. We're talking about 10 times more, 10 times less for the extreme outliers here. We can predict a lot of information from this. We can predict a lot of stuff about how much energy homes are likely to consume given publicly available data. And this, lastly, I do want to stress again the point that this is really simple machine learning. I mean, we've already covered all that we need to know for this paper here. Maybe some of the probabilistic stuff not quite as much, but basically the same thing. It's different loss functions. And so there really is a really big value to machine learning techniques to practitioners, people that want to understand data. And so these techniques really can even applied simply, if they're applied correctly, can make have a very, very big impact on how people understand the data regarding energy consumption or anything, really. So that is it. And that also concludes our unit here on machine learning. So congrats, you made it through the first third of the course. So I guess only a fourth of the homework so far, and then none of the project yet, so maybe not quite. A third of you're watching me talk, though. So that's all for machine learning. And before I move on to the next topic entirely, which is going to be a big departure, are there any questions about anything at all about machine learning? Okay. Well, if you have more questions, come ask me. All right. So let me now, we won't have too much time for this, but let me at least get started with the next unit in this course, which is electric power systems. So if you remember the first lecture in class, what I said was that the first 2 units really in some sense are about simulation or prediction, right, of power systems. So I mean, this is a smart grid course. We're going to cover some machine learning. We're also going to cover some actual power systems, given that is the laws that dictate the grid. But the first 2 things I said were actually more related than you might think, because they're both really about making predictions. So the first set of predictions are things like how much energy people are going to use tomorrow, given the high temperature, the predicted high temperature, or hours a day, or whatever. And these are the things that would be very hard for anyone really to just think enough about that and write down some laws without ever actually looking at any data to tell you how much power we're going to use tomorrow. That's something that's very hard to develop a priori models for, right? In contrast, if you were to say, if I turn on these generators and I have these transmission lines, what's going to happen? Okay, that's also kind of a prediction question. That's good to know, right? Am I going to fry this transmission line or not? But you don't want to do that by running a lot of tests and seeing what happens. I mean, you probably don't want to just turn on generators and say, oh, look at that, it produces this much power. This power flows this way. It's amazing. Unlike things like total demand, which depends on human factors, is inherently kind of hard to predict, things like the actual physics of electricity are very well understood from first principles, right? We can write physical laws that actually tell us with, there's certainly some amount of things that we don't know. Maybe we don't quite know the exact resistance of a line or things like that. But, we can measure these things pretty well. We can get a very good understanding of the principles governing these physical processes to the point where we actually want to use laws of physics rather than, machine learning to try to predict these things. So what this unit is about, and as I say, it's going to be a big detour, so we're making a major shift, not detour, but a major shift now, is going to be about really the physics of the electrical grid. Because when you talk about the smart grid, it's really important to have both these concepts, sort of to have a mastery of both these things. Because there are plenty of phenomena that we can't predict using physical properties, but we also want to, whatever we can predict with physical properties, we want to do that. So both these things are kind of 2 different elements of the smart grid problem. So, remember I started off talking about this slide here, about how we use energy. And the point I would want to make here, more than anything, is that a lot of this energy that we use goes through electricity. Electricity is very high value, as I mentioned before. We can basically do anything we want with energy. We can do with electricity. That's not vice versa. Heating energy is kind of low quality in some respects. We can heat up a house, but you can't really do much more than that. So we want to talk about what happens to this big chunk of electricity generation there. Another thing you notice is that a very large portion of that is designated here as rejected energy. So this is energy that sort of isn't being used somehow. And some of this is just unavoidable. You can't get perfect conversion from fossil fuels to electricity. Like, you lose something when you do that. But there also are inefficiencies that we can address. Can we schedule energy better to make better use of the more efficient generators, for example, the ones that have a higher efficiency? Some have the efficiency of well over 50% or so. So can we use those? Maybe not that much over, but 50% is reasonable. Can we use those ones instead of the really bad ones? Can we maybe transmit energy less distance so we don't have to have as many losses in the transmission lines themselves? But also, it's good to know sort of where our electricity comes from and where it goes. So these are sort of that incoming. This is a pie chart of that incoming little slice there, and then also we're going to have a pie chart of the outgoing slice. So in the incoming slice, I talked about this before, but basically, maybe 4% comes from what we would think of as renewables, like wind, solar, and geothermal. 6% comes from hydro, but we've dammed up most of the rivers that we really know about or can easily do so far, so that's not going to grow a huge amount. And the rest comes from fossil fuels. So this is electricity now. Before I was showing, I showed a graph a long time ago about total energy, and then that was like 1% was wind, contribution of wind or solar. When you look at just electricity, which is really the only place that wind and solar goes, that's now about 4%. So this is good. This is definitely growing, but we certainly have a long ways to go to get to a what we would think of as a sustainable energy infrastructure. About half of it still comes from coal, and probably what's going to happen is that's going to go down, but this chunk here from natural gas is going to go up a lot also. So, less of one, more of the other. And also, in terms of where this goes, it's pretty evenly split amongst industrial usage, residential uses, and commercial usage. So commercial would be buildings like this, office buildings, things like that, and also just commercial storefronts, stuff like that. Industrial are like manufacturing, this kind of stuff, and then residential is homes. And so a lot of it, homes and buildings, commercial buildings, are really actually a very big chunk of this. Very little is used for transportation right now. There's some, but there's very little electricity used in transportation currently. So to get an idea about all of this, or sort of a better understanding now, we're going to delve into the actual physics of electricity. And many of you have probably seen this already, so for many of you, this will probably be actually, or for some of you, this may be a review. For those of you who have seen it, for those of you who have an ECE or EE background, this will probably be very, very basic. But maybe for those that had some machine learning before, this will be the hard part, and for those that had some of this before, machine learning was the hard part. So the course balances out to a certain degree. So start off with, and I have 20 minutes left today, so I'll get through a little bit of this, but not very much. Actually, again, sort of as a survey, who has taken a basic course on electricity here, or some sort of physics of electricity? Okay. It can be a long time ago even, it's fine. But we'll go, as I said, the stuff we're talking about here is extremely basic, so if you haven't seen it before, it's actually completely fine, but a lot of people have. Who here is, so people know about DC circuits mainly. People look at AC circuits also, show of hands? Okay. What about AC power, things like real and reactive power? Okay, so less people, but that's good, so we'll cover that. And then power flow, does anyone? Okay, so one person that sort of is this is going to be the easier part of the course then, I'm sure, but we'll go through it all. Okay, so some basic sort of, I guess this is probably like grade school physics here, right? Certainly no more than high school physics. But there are a couple of definitions. The first one is charge. And charge is sort of this, sort of this amorphous thing, right? It's the property of matter that causes it to experience a force when it's near other charge, right? So positive, two like charges will repel, and unlike charges will attract. And charge is measured in coulombs. The unit is coulombs, which is the charge equal to some large number of protons. I actually forget exactly why they picked that number. There's some significance to that, but that's what one coulomb is that many protons. Voltage is really electric potential energy. And the way we're going to define it actually, it's measured in something called volts. And we're going to denote it as the symbol V or V. It's actually one of the few things where the unit is the same as the symbol we use for it. So usually like current, we'll use I for current, but it's measured in amperes. So we'll get that in a second. So voltage is electric potential energy. And the really way to think of that is 1 volt is 1 joule, which is a unit of energy, per unit charge. So it's the more voltage you have, the more energy there is in that charge. And the common analogy here is something like water flowing through pipes, where the voltage would correspond to, say, the height that you raise the water of. So if you raise water to a really high height, that has the ability to do a lot more work, right? Because it can flow down and do all this work. Whereas if you have it at a lower level, it has less ability to do work. So voltage is kind of like the potential for this charge to actually be released and act and do work. It's important to know that voltage, though, really is a matter of difference in potential energy. So we really want to talk about voltage drop between different points. So it's just like with water, it doesn't really matter how the absolute height of a bucket of water. What would matter is the relative height between where you have it at and where you pipe it to. That would be essentially what really matters. And similarly, voltage, we're really talking about the difference in voltage between two different points in a circuit, say. Current is the flow of charge. So current is actually the flow of how much charge is moving through a wire. And the water analogy, I'm going to stop with the water analogy pretty soon because they get really old quickly, and when you start talking about AC, there's just no real actual equivalence anymore. So I won't push it too far, but it's good to think of it at first. So the current is the flow of electrons, but really the flow of charge through a material. We denote it with a symbol little I or big I, and it's measured in amperes. And amperes is a unit of coulombs, unit charge per second. And so the water analogy would be, you have a pipe, how much water is actually flowing through that pipe per second. Right? That would be the analog of the current. And unlike voltage, which is measured at 2 points, what we care about is the difference in potential energy. Current is really measured at a single point, right? Just how much charge is flowing through that point right there in the circuit. Now, given these two definitions, the formula for power, electrical power, becomes fairly obvious. Because a volt, remember, power is measured in watts, and 1 watt equals 1 joule per second. Right? And current now is going to be coulombs. Coulombs. Man, I'm not doing this well today. Coulombs, 1 coulomb per 1 second. This is current. Voltage is joules, 1 joule per coulomb. So the product, this is current, this is voltage. So the product of current and voltage is electrical power. That's just really comes from the units themselves. And it's almost definitional. I mean, it's, a volt is really defined as potential energy per, energy per unit charge, and current is defined as unit charge per second. So their product has to be power. And this is the formula which we'll use again and again here is the power equals the current times the voltage. Now, we're going to start drawing symbols for circuits. So I'm going to start drawing some circuits. Talk about what happens when you hook up a circuit this way. And two things that I'll draw in these circuits, though I'll draw one a lot more than the other, are voltage sources and current sources. So a voltage source is something that maintains a fixed voltage drop across its two terminals. And a current source is something that maintains a fixed current through that point. So here where's my long eraser? I use that as like a pointer. Oh, here it is. It has a pointer too. So this one here is saying the voltage drop across that thing is 10 volts, and this would be saying there are 10 amperes flowing through that point in the circuit. A good model for a voltage source is a battery, because at least with that, when they're not too heavily loaded, batteries act approximately like voltage sources. Or in fact, for an AC voltage source, something like an electrical outlet would be a very good model for that, because they approximately maintain a constant voltage, and when you hook stuff up, the voltage doesn't change, just more or less current flows based on whatever you hooked up to it is. We'll get into that in a second. Current sources are a little trickier. There aren't that many good analogs. There aren't that many things that sort of ensure a fixed current flowing through a wire and set the voltage to be whatever it wants to be to attain that current. That's a little bit less common, though some things actually like solar panels are sometimes very good. Sometimes things like current sources are actually very good models for things like solar panels. Not quite, but they actually can be. So there are instances of this thing, but we're going to mainly deal with voltage sources for the most part. One symbol which you'll see a lot is a symbol called ground, and that's this little guy here. It looks like this. And what that does is, remember, voltage is only defined in terms of a difference between different points, right? So it's useful to actually have some reference that we say this point here equals X volts. And in the case of ground, it's saying ground is equal to 0 volts. So whatever the potential is, we just call that 0 volts. The origin of this is that the ground, the earth, is actually a pretty good sink for a lot of energy, so for a lot of electricity. So if you do connect a wire, say, to ground, the actual physical ground, that would be a reasonable way to say that, that there's not going to be any potential difference between here and a similar wire plugged into the ground elsewhere. So we just fix that reference to being 0 everywhere. It's not quite the same. Ground in a circuit really is the same everywhere. 0 resistance between all of them. There's no current flowing. You don't want to actually stick wires into the actual ground the way you do with the grounding here a lot of times, but we won't worry about that. Just for our sake, the signal will mean this points always are considered to have 0 reference voltage. And finally, the last, I think, element of DC circuits is called a resistor. We'll get to more complicated things for AC circuits, but for DC circuits, resistors are kind of the main thing you think about in linear circuits in the DC case. So a resistor, by nature, as you probably guessed from its name, it in some sense kind of resists the flow of electricity. So it doesn't want to have electricity, doesn't want to have current flow too fast through it, kind of resists the flow of current. It's measured in ohms, which is the symbol, we're going to use the symbol R to talk about, ohms uses the symbol omega to denote ohms, and we're going to use R to denote resistance in the circuit. And rather than, an ohm is 1 volt per ampere, but actually don't even think of it that way. The way to really think about what a resistor is through this formula here called Ohm's law. And you can think of it this way. It's the voltage equals the current times the resistance. Another way to think about this is just that the current equals, because we often think about fixed voltage being fixed and resistance being fixed and current being the thing we're trying to solve for, you may have seen a more common form, which is just, of course, it's the same thing, but I equals V over R. So what this says is that if you have a fixed voltage, you put it across a resistor of a certain resistance, this much current will flow through it. Do the same thing here, where if you have a certain current flowing across a resistor, the voltage difference has to be this across it. Those are equivalent. But this is really how to think of resistance. Resistance says how much current will flow through something given a voltage drop, or equivalently how much a voltage drop is there going to be given a certain current flowing through it. And in a diagram, remember, we have some signs for that and signs for voltage sources. We're going to draw it like this, a little jagged line here to denote that, I guess, current has a hard time going through that. OK, so let's look at some example circuits now. Here is a simple DC circuit. So we have a voltage source, which is a 5-volt voltage source. It maintains, oh, and I should also mention, the notion of current, of sort of the flow of current, it's actually kind of arbitrary which way current flows. It could flow from positive to negative or negative to positive. This is sort of a big thing, actually, because physically what happens is that the negative side of a battery is the one where electrons kind of build up, and the electrons actually move from the negative terminal to the positive terminal. We're not going to use that convention. We're going to use this sort of more standard EE convention, which is positive current flow. So current flow actually flows from current flow, whatever that means, flows from the positive to the negative terminal in all our examples here. So that's what current is. That's sort of the standard everywhere. I guess who got that wrong originally, like way back in the day, and it's like this forever. So if they had just flipped it, it would have been much simpler, but oh well. They're arbitrary entirely, right? Positive or negative doesn't make a difference. So anyway, here is the DC circuit. So we have a voltage source, 2 resistors here. Each of them are 10 ohms. We have a ground here. That's all the symbols we've talked about so far. Now, the goal of what I'm calling linear circuit analysis, and we'll get to why it's called linear circuit analysis in a second. I guess I have it right here in the next thing, is the following. If we're given a circuit where we say know the resistance is, and we know maybe some of the voltages or some of the currents, some collection of voltages and currents. Find the rest of the currents and voltages. Okay, so a simple example would be, in this case, we know the voltage, we know the resistance, find the current that flows through this circuit here. Okay, and this is pretty easy because, well, actually, I won't get to how those two things combine just yet, but it's very easy to do here. And it's called linear circuit analysis because there's actually always a solution that can be written in terms of this exact equation here. This is just Ohm's law, but I'm replacing R by this Z term. And also the thing I'm doing is I'm now talking about not just one voltage or current, but actually whole vectors of them. So now V and I in this formula here can actually themselves be vectors of currents or voltages. What this is saying, and we'll talk about this a lot later, so don't worry about the details now, is that if we look at currents and voltages at different points in the circuit. So, what's the current, what's the voltage drop between here and maybe the top, or between the middle of those two things and the top? If we write these things down, and in this case you don't have to, because this case is a really simple circuit, but if you look at a big circuit and treat voltages at different points as being elements in this big vector V, and currents at different points being the elements in this vector I, those two things are linearly related by a matrix that's analogous to sort of a matrix version of the resistance. Okay, so all of sort of linear circuits, and I'll talk about what I mean. It'll hopefully become more clear what I mean by linear. Basically, linear circuits are linear if they satisfy this. If they don't, then it's nonlinear. But for the most part, things say with just resistors and voltage sources are going to be linear. Then in that case, the voltage and current satisfy this linear relationship. Now, it can be hard, or at least not that easy, to sometimes define this matrix Z in terms of the different resistor components in the circuit, but they can always be set up in a way that these linear relationships hold here. This is why we call it linear circuit analysis. The same actually is true for AC too. Even though you think of AC as having sinusoidal currents, it turns out we can do the same thing for AC circuits. So AC and DC circuits can both be analyzed through linear circuit analysis. That's all I'll say for today. We're 2 minutes left, so I'll pause now. Next time, we'll start talking in much more detail about DC circuits, how you actually compute or maybe even practically solve them, even if you don't want to go through the rigmarole of actually computing these things. How can you solve them on a computer, say? And then we'll talk about the AC case and how these same things extend to the AC case. So, okay, see everyone next time. Remember, no class on Thursday. Class next Tuesday.